Hi, and welcome to this new video on another research paper that's Deep Recurrent Q-Learning for partially observable MDPs. So again, in the previous research paper, I talked about how deep Q networks, DQNs, or deep Q learning methods were evolved. Initially, they were very basic and were not very good performance, were not giving really good performance at all. But after some modifications, we saw that DeepMind's paper showed how they can make some improvement using experience buffer and some other small tricks. The reason I'm talking about the previous one is because this paper that we are going to talk right now about is going to be a basic extension of the same. How exactly? We'll look into that very soon. But you can understand this as how they are overcoming the shortcomings of the previous DQN paper by introducing some or just one recurrent layer on top of it. So what exactly are they doing with it? Let's try to uncover. This video, I'll try to make sure that it's shorter than the previous one. Previous one was around 35 minutes, which I think in my opinion is not really a small amount of time that viewers should give to just one paper. You should be able to get an overview of papers very quickly. So I'll try to make sure that this one is smaller and upcoming videos are also smaller. Anyways, coming back to this paper, what main difference that we see from the previous implementation of deep Q networks to this one is that they are adding recurrency to the deep Q networks by replacing the first pre-convolutional fully connected layer with a recurrent LSTM. What is LSTM? I hope you guys, everyone understands basic deep learning terminology, and LSTM is basically long short-term memory algorithm. It's very popular. If you do not know about it, there are tons of videos on YouTube and everywhere. You can definitely check that out. Probably it will hardly take 2 or 5 minutes to understand it. At least have a basic overview. And that will be enough. And that's the only change that they are making. That is it. And what does that mean for us? That after introducing this one small change, that converting the last or first post convolutional fully connected layer with this recurrent LSTM, what they have achieved is that what DQN used to do with 4 frames stacking. Remember that one state was basically 4 different frames, concurrent or 4 sequential frames were combined and called as one state. In the previous paper I'm talking about the older one. This time they have achieved similar or almost the same results with single frame. So over here they are considering each frame as one single state instead of just 4 of them. And what is this? What is this partially observable MDPs? What are these partially observable MDPs? Or we often call them as POMDPs in literature, like it is mentioned over here, POMDPs. And how do they create them? I'll talk about that later on very soon. But they found something very interesting happening when they introduced this recurrent neural network on top of the CNNs and DQN network that already existed. Fine. So they call it DRQN now. And I'm not sure what they have exactly proposed here or not. I think they're coming up with 2 different networks. I'm kind of unsure. I'll just make sure that I'll get into the details and come back to the video description later on. But what happens is, by the end of the paper, I read about how they're introducing 2 different networks, DRQN as well as an improved DQN. The thing is, it could probably be my own misunderstanding or something, but they are using them as 2 different models. Even in the comparison, you see, DQN, which was the previous one, and the one that they have implemented, as well as the DRQN that they are introducing in this new paper. So pretty interesting stuff. I have not seen anyone do this thing before. Probably it could be because I'm kind of novice here in this multiple algorithm introduction thing. But anyways, the point being that they are in total proposing 2 different things, and both of them, some or the other way, try to outperform the traditional Dukan that we saw in the previous one. So let's interpret this first. Over here, DRQN and DQN, the modified DQN, that is their paper. So DRQN and the modified DQN are combiningly outperforming the traditional DQN in most of the cases, but in some cases, traditional DQN is performing better. For example, over here, it's performing better. It's performing better here as well, here as well. Pro statistics, I forgot the number of games, but I think their approach wins in like 5 out of 9 games, and yeah, that's what their conclusion is, which may not seem a lot, but I think my personal opinion is that their approach outperforms the traditional DQN in partially observable MDPs. Now, as I'm coming up with this partially observable or POMDPs environment, this partially observable environment, I'll just call them POMDPs now. So I hope you all understand what a Markov decision process is. I think we have already discussed about that in the previous video, but not much in detail. But if you want another video on just MDB, just let me know. I'll get that covered. What we are more interested in this video is partially observed. Fine. So what they are saying is recurrency is a viable alternative to stacking a history of frames. So recurrency will basically try to find correlations between each frame. This means that recall again that why did we really need for frame stacking at the first place, right? Why did we need that at all, right? Because just having a single image will not tell you in what direction the agents or opponents are moving. For example, in the Pong game, just looking at this one snapshot, can you guess sorry, can you guess in which direction the ball is moving, or left or right? Well, it becomes kind of impossible to tell in which direction this ball is moving, because it could be moving in the right direction, left direction, it could be moving diagonally, it could be moving in any way, like in any possible way. Similarly, over here as well, we don't know whether character is moving. Stacking different number of frames, like 4 frames at the same time, will give the neural network a better idea of in which direction this movement is taking place. So that was the primary reason that why we used to stack those frames. But with the introduction of recurrent neural networks, this recurrent LSTM, we could say that okay, it's a viable alternative to stacking history of the frames, while it also confers no systematic advantage on top of basic DQN. So they also tell that it's not extremely better. It's not doing the whole motive is not to build DRQNs better than DQNs, but basically provide an alternative. And why is this alternative essential? Because it better adapt at evaluation time if the quality of observations change. What do I mean by quality of observations? So, in older times when television was new, when these games were new, the screen might flicker sometimes, right? So, the flickering of screen is a kind of a big issue, and that's how they're introducing partial observability as well in this domain. Ideally, we want the screen to give us frames at every single moment, every single state. We should have one particular frame in front of us. But what if the frame that we see in front of us is blank? It could possibly be there, right? So I don't know how can I give you a better example, but let me try. So imagine that you are standing here, and there is a bottle in front of you, and there is a mobile phone that's behind it. If you want to operate this mobile phone, you cannot really do it, or you can just partially observe this mobile phone, but that does not mean that you cannot really unlock it, you cannot really operate it at all, right? Humans are good at adapting to these different observation qualities. We know that even if we are able to observe something just partially, then also we'll be able to operate on it. But robots or AI does not really yet know that how to complete an incomplete observation. And Probably that's what partial observability also means here. The thing is, how are they introducing it in this context? Excuse me, I just have a little bit of cold as of now, and that's why this video took a really long time to upload. Well, I need to edit a lot of things. Anyways, I'm looking at flickering. Yes, so flickering pong. This is basically a POM DP, and how are they introducing it? At each time step, the screen is either fully revealed or fully obscured with probability 0.5. It's flickering and with a probability of 0.5, which in my opinion is really big because at a limit, you can think of it as the robot or the AI is not able to see the observations for almost half of the time that it is playing the game, and it has to make some assumptions in that case in what direction the ball might be moving just because the AI does not have previous or multiple of the previous frames at all, because this probability is zero point 0.5 and it's completely random. There's a huge chance that it will never see next frame or the previous frame. It will just have to do with this one single frame and just believe in its algorithm that okay, it might have learned a good policy or not. Fine. So that's why I think that this is a really huge leap if they have successfully implemented this. And or what's obscuring according to them they have shown here, and this just basically means what I said. So this flickering pong, it is necessary to integrate. So why so how can this AI achieve a good policy? So how the flickering pong is working here is that the AI needs to integrate information across multiple frames in order to estimate the relevant variables such as location of the ball or the velocity of the ball or location of the pedal, even if that information is completely blank in front of it. Fine. So these are different things that the AI should learn, the AI must learn in order to succeed in such games. And this paper is published, so we know that yes, it works. That was spoiler basically. Fine. Okay. So remarkably, I'm just quoting their words so that I don't get into any trouble. DRQN performs well at this task even when given only one input frame per time step. That's what we talked about while I was showing you the abstract of this paper. And I think this is one of the biggest achievement of this paper, according to me, that you don't need to stack different frames. You can understand the pattern of things moving around in this environment from previous frames, not because you have stored it, but because you have learned it. So there is a difference, right? Another thing that I would like to quote is individual units in LSTM layer are capable of integrating noisy single frame information through time to detect high level Pong events such as the player missing the ball and the ball reflecting on the paddle or the ball reflecting off the ball. So it's actually mentioned, it's actually shown very well in this image as well. So these are the learnings by convolutional network that they have given over here. Here is the architecture: convolutional layer 1, convolutional layer 2, convolutional layer 3, and then there's LSTM at the end. Then there are Q values at the end. Fine. So basically, first layer learns this these features, second layer learns these features, third layer learns these features, and so on and so forth. Image sequence maximizing 3 sample LSTM units. So let's zoom in. You'll see that there is this bouncing on the wall. There has to be some yeah, over here it's missing, so the pedal is missing the ball. So there is no pedal, it's just probability of the pedal. It should have been there, but it's not. There is, I want okay, reflection to the pedal. This is what I wanted. So this is interesting because you'll see that there is this pedal, and if the ball is coming from here, we would expect it to go in this direction, that is away, right? So we want that to happen. So if we want some sort of a mirror kind of a reflection instead of this bouncing back in like in an acute angle way, we don't want that, but that's what we must have thought of. what is actually happening here is it's interesting because this is an unusual pattern that humans might take a while to understand, but with sufficient training, neural networks have learned this, which, in my opinion, I think it's kind of fascinating because if the pedal is moving and if you touch its edge, the pong will not move in any reflection kind of a way. It's not following the law of reflection or anything, but it will move in some acute angle, and it is trying to shoot the ball such a way that it moves somewhere either away from the opponent or moving in a direction such that it moves towards the edge where it becomes difficult for the opponent to reach. Fine. I'm not sure if I'm explaining that well or not, but whatever for now. So this is what is happening. Okay, so what they talk about is that any 4 frames of input, if you give it, all of these games will become MDP instead of POMDP. So that's why, according to them, that's why DQN had some edge in the beginning because it does not really work well with single frame. But that was basically converting it. So, in my opinion, I think that it was not a fair fight because DQN was always using 4 frame stacking. Because DQN will not work without that, and DRQN was using single frame input at every single time step. It might have some disadvantage as compared to DQN, but I'm not trying to compare DQN with DRQN. I'm trying to defend DRQN in a way that it has achieved something probably as good as, not surpassed or not outperformed DQN in any way. It has almost matched the level of expertise that is learned using DQN, if not surpassed it. So there are several places it has surpassed the way, and this is kind of I don't know about this game, but the games that I know, DRQN is not performing too good. But honestly, I don't think competition was the objective at all. Fine. So a lot of related work was going on. Something that I would like to discuss most is, oh yeah, the architecture. The architecture is similar to what we saw in DQN. By the way, this is a brilliant book. You should read it. Yes. Learning control policies for, so this is what deep Q learning is, basic idea around it. I like this paper because I feel that it gives you a good introduction to an entire deep Q learning architecture, how things were beginning. I also like the related work part. They have given good references, citations to nice work. Like for example, Narasimhan Kulkarni did a good job. I read this paper. I might be reviewing it in the next one. Not sure. We'll talk about that later. But if you want to stay connected and see which paper I'm going to review next, go and check out the GitHub repository in the description. I will go in that sequence mostly. If I find something extremely interesting in between, I might skip a few and take the interesting paper ones. Fine. So this was a whole point of having recurrency in the neural network. So the key hypothesis is that the DRQN can better handle partial observability because it leverages the memory capabilities of recurrent networks. Well, also the core idea is that recurrency offers an alternative of stacking that I talked about in input layers of DQN to deal with partial observability problems. So honestly, that is it about this good paper. And yeah, let me know if you have any questions in the comment box below. I'll try to address them. And if you want me to go through the papers in much more depth, I'm planning to introduce coding as well, but from the next video onwards. Introducing coding would definitely deepen the understanding of the core concepts, but it will also lengthen the videos. But whatever you are okay with, I am open to new ideas and suggestions. Let me in the comments below and I'll get back to you. This is a basic introduction or basic overview of this paper. I highly recommend you read this paper once you have read the previous one. Even though if you have not read the previous one, this is not a bad idea to start with. But this is a gem. Like this part, I love this part. The way they have explained this entire MDPs, POMDPs, and everything. I think this they have done probably better job than the previous papers. So sorry, but yeah, I think this is a good crash course on deep Q learning. Everyone should read this part. When I read this paper for the first time, I could not believe that someone could simplify this concept so well, but they have done a tremendous job in this section, as well as defining and implementing partial observability, their thinking process of how this is true. Um, yeah, so they have explained it here. A lot of different things I liked about the paper, which I could not discuss in this video. I want it to be around 15 minutes, not much, but I'm pretty sure I'll exceed that. Anyways, but I want you to definitely go through this paper, have a basic outline of it, try to understand as much as you can, and let me know if you have any queries. The entire paper is very well written and is extremely beginner friendly. So even if you are new to deep RL, you can definitely check this out. So until then, have a great day and take care.